Guys, Mr. Carlson here. Let's talk about forces on an inclined plane. That's what we're talking about today, the inclined plane. If we look here, we have a model of a block sitting on an inclined plane, which is basically just a hill. What we want to remember for this is that whenever we've got something on an incline like this, gravity, here's the force of gravity, would be represented by this arrow. The force of gravity is always pointing downwards, straight towards the center of the earth. So as I change the angle of this arrow is always going to be pointing towards the center of the earth. This arrow here, which represents the normal force, that always has to be perpendicular to this surface. The normal force always has to be perpendicular to this surface. So if I were to change the angle of this, if I were to bring it lower down here, if I were to bring it at a steeper angle, this arrow always has to be exactly perpendicular or at a 90-degree angle to the surface of this. Now, the other thing that can be tricky about this is that this force of gravity right here is going to be broken up into two components. So there's two things that gravity is doing in this case. Gravity is holding the block to the surface, right? So there's this component of gravity that's pulling the block to the surface of this. The other thing that gravity is doing is it's pulling the block, making the block want to slide down the hill or down the incline. So we're going to take this force of gravity and we're going to break it up into this component here that is holding the block to this surface. And so I'm just going to label that as Fg, and I'm going to say y because it's in the y, part of the y-axis. And then this component right here, that we're going to label as Fg as well, but we're going to put x because it's part of that x-axis. So gravity is broken up into these two components. We've got normal force that is always perpendicular, and then we also have this force here, which is going to be the force of friction. The force of friction always has to be parallel to the surface of this inclined plane. Some problems, they tell you to ignore friction. You don't have to worry about that. But in some problems we do. So this is our basic setup for this. And the other important thing that we have to remember is that this angle here, whatever the angle of the incline is going to be the same as this angle here. Whatever angle that I've got here has to be equal to this angle between the force of gravity and my force of gravity on the y-axis here. Basically, that angle and this angle are always going to be the same. So let's take a look at this first example right here. We've got Billy and Carl, and Billy is sliding Carl. Carl is a box, by the way. He's sliding Carl, which is a 3-kilogram box, down a smooth, frictionless incline that has an incline of 30 degrees. They want us to draw FBD just means free body diagram. It's just another way of saying a force diagram for the box. So if we come up here, we'll just take this, and in fact what we'll do is we'll just use this for our free body diagram, except for this one is frictionless, so we're going to get rid of friction in this case. And so this would be our free body diagram, or our force diagram for the forces that are acting on this box. And we're going to make this angle 30 degrees, which remember we said if this angle of the incline is 30 degrees, this angle here is also 30 degrees. And so there's my force diagram here. I've got my normal force acting on the box, and then my two components of gravity that are pulling the block this way and holding the block to the surface of the incline. So there's my free body diagram. Now, we want to calculate what the normal force on the block is. We want to calculate what this force is. Well, since the block is not accelerating along this y-axis, right? It's not moving upwards, it's not moving downwards. And so this these two forces here need to equal out. My force of gravity in the y direction needs to equal out the normal force. And so what I'm going to do is I'm going to use some trigonometry here, solve for what this force is, and once I know what this component of gravity is, I automatically know what this normal force has to be. So what I'm going to do is I'm just going to draw, I'm going to take these two components and this one right here, and what we're going to do is we're going to make this into our triangle. So I'm going to draw it over here, make it into our right triangle so we can solve for this. So we've got the y component here, and what I'm doing is I'm taking this component, the force of gravity in the x direction, and I'm just sliding it down basically to make a right triangle with this component and this component. So there we go. So here's this is our right angle here, our 90-degree angle, and then this angle here, remember, is this one here, which is 30 degrees. So 30 degrees. This is the force of gravity right here. Now the force of gravity we know is just going to be 10 times the mass, so 3 times 10 gives me 30 newtons. So that's this part of that triangle. I'm going to label these. So this right here is going to be FGY, and this is going to be FGX. Now what we're trying to figure out is normal force. So I want FGY. I want this one is what I need to figure out. So if I look, here's my angle, 30 degrees. So I'm looking at the adjacent side, and I've got my hypotenuse. So adjacent and hypotenuse, I should write these up here so we have them. So TOA. So we're looking at adjacent and hypotenuse. So I'm going to use this cosine here. So we're going to come down here, and we're going to say that cosine of 30 degrees is equal to my adjacent side, which is FGY, the force of gravity in the y direction, divided by 30 newtons. And so to solve for this, I'm going to have to multiply each side by 30 newtons. And so FGY is going to be equal to, let's see, cosine of 30 times 30, and we should get 26 newtons. And so remember, so that is this component, that's going to be equal to my normal force. So my normal force is also 26 newtons because the box is not accelerating along this axis here. Now the final part, part C, it says find the acceleration of the block. Well, we know using Newton's second law that acceleration is equal to the net force divided by the mass. I know the mass of the block. Now we got to look at what's the net force. Now be careful here, because what we're really looking at is the net force along this axis. So really what we're interested in is this component here, and if there were friction, we would have to account for that as well. But in this problem, it's frictionless, and so really the net force along my x-axis here is just this component right here. So if I can solve for what this force is, I know what my net force is along this axis. These forces cancel out, and so they're not contributing to what my net force is. So it's just this one. So we come back over here. We're looking for this force of gravity in the x direction, what's pulling it down the hill. We're going to solve for that. So that's going to be my opposite side over my hypotenuse. So sine of 30 degrees is going to be equal to FGX divided by 30 newtons. And so we're going to take 30 multiplied by each side. So the sine of 30 times 30 means that FGX is equal to, let's see, 15 newtons. 15 newtons. So this component right here is 15 newtons. There's no friction working against it, and so there's my net force pulling the block down the hill. So to find the acceleration, I just got to plug those numbers in. So acceleration would be my net force of 15 newtons pulling it down the hill, divided by the mass, which is 3 kilograms. And so my acceleration is 5 meters per second squared. Remember that newtons per kilogram is the same as meters per second squared. They're both units for acceleration. And so there's my final answer there, 5 meters per second. Or sorry, 5 meters per second squared. Let's take a look at another example. In this one, example 17, we've got Jonathan pushing this same 3 kilogram box out of the ditch. So this time he's pushing it up an incline. So now we've got this incline like this, and he's actually applying a force on the box up the hill. So we've got a force applied like this, pushing up the hill. And once again, they're making it kind of easy for us. It is frictionless, so we don't have to worry about the force of friction here. And it's a 30-degree angle again. So here's our hill that he's pushing it up. This angle here is 30 degrees. And they tell us that he's pushing with a force of 40 newtons. So this force applied right here, we'll say, is 40 newtons is what he's pushing with. First thing is they want us to draw a force diagram. I'm just going to draw it up here on this. And so we've got, remember, gravity is going to be pulling straight down. Normal force has to be perpendicular or at a right angle to this. So I'm going to draw for my normal force at a right angle, perpendicular to this surface. And then remember, we're going to break this force of gravity right here. We're going to break this up into two components. The component that pulls the box to the surface of the hill, and then also the component that is pulling the box down the hill this way. So we've got force of gravity in the y direction, and then force of gravity in the x direction. And I should label this normal force right here. Okay, there's my free body diagram, or my force diagram for this situation, because I don't have to account for friction either. Part B, let's find the normal force on the block. So again, what I'm going to do is I'm going to take this triangle, I'm going to redraw it down here to make it a little easier. Let me redraw, hold on, that was a bad, this should be better than that. So that's even worse. Let me try one more time. Straight down, that's just going to have to do for now. So there's our force of gravity there. We're going to take this force like this. And then this one, we're going to move down here like this to make our right triangle. So it's going to look like that. Here's our right angle. This angle here, this would be right here, has to be 30 degrees. We know that this force here is going to be 3 kilograms times 10. So once again, 30 newtons, just like the previous problem. And so we're solving for this one right here, force of gravity in the y direction. That's what we're looking for here, because again, we're trying to solve for the normal force. We got force of gravity in the x direction. So the normal force is going to be equal to this one. So let's see, we've got adjacent and hypotenuse again. So we've got cosine, right? So cosine of 30 degrees is equal to FGY over 30 newtons. And so this is going to be the same as the previous problem, actually, because it's all the same stuff. We've got the same angle, we've got the same mass of the box, and so this is actually going to work out to be the same normal force as the previous one, so 26 newtons. So 26 newtons pushing up. And we want to find the acceleration of the box. Now this one is going to be different than the previous problem, because in this one, we're now pushing up the hill with 40 newtons of force. So in this case, I want to figure out what's the net force now along this axis here. I've got 40 newtons pushing up, so now I need to figure out what is working against those 40 newtons. So I got to figure out what's the force of gravity in the x direction. So let's think about that. That's going to be right here. So that's going to be opposite over hypotenuse. So that's going to be sine of 30 degrees is equal to opposite FGX over my hypotenuse, 30 newtons. So multiply by 30 on each side. My force of gravity in the x direction is going to be 15 newtons. And so now what we want to do is figure out what's the net force along here. Well, I've got 40 newtons this way. I've got 15 newtons this way. So net force would be 40 newtons minus that 15 newtons, right? Because they're acting in opposite directions. So I'm going to subtract them from each other. And so the total net force that this box feels is going to be 25 newtons. That's what's left over. And it's going to be pushing up this way. So we could say like 25 newtons up the hill is what we'll say. 25 newtons up the hill is my net force. And so now we can use that for, in my Newton's second law equation. Acceleration is net force, which is 25 newtons, divided by the mass, 3 kilograms. And we are going to get 8.3 meters per second squared. And that's the rate at which this box would accelerate. As long as he's applying 40 newtons of force the entire time, that's going to be the rate that it accelerates up the hill. And the last part here, how would the acceleration of the box change if the incline was steeper? So if we had a steeper incline, if we were to make this like maybe, let's say, a 60-degree angle, what would the acceleration, and I guess we're assuming that the force is still 40 newtons. So you're still pushing with 40 newtons, but now we make this incline up to like 60 degrees. Well, in that case, the acceleration would have to go down, right? Because if I increase this angle, what I'm actually doing is making this component of the force of gravity, I would make that bigger, wouldn't I, as I increase this angle? This force here would get bigger and bigger, and that force is what's working against this 40 newtons, and so my net force would get smaller and smaller, wouldn't it? And so what we could say here is that the acceleration would decrease. Acceleration would decrease. And we could say because as the angle increases, we'll say FGX increases, which would make my net force a little bit smaller, which would make my acceleration even smaller. And that's where we'll stop for this one.